Hello everyone, we will talk about the induction motors today. It has three different names. The first name is the induction motor because of the induced voltage on the rotor side. So before that, maybe we should talk about the construction of the induction motors. We have three main parts. The first part is the outer part of the system, which is called as stator. And inside this, we have the rotor without a physical connection with stator. And between them, we have a very thin gap. We have air gap between them to transfer the magnetic field from the stator to rotor part. So the induction motor's induction name coming from the stator magnetic field will induce a voltage on the rotor part. Because of that, the induction name is coming. Asynchronous, the magnetic field which is produced on the stator part will be faster than the rotor speed. So because of this, the speed difference between the stator and rotor, the name of the machine is also asynchronous motor. And the rotating transformer. Why? Because when we examine the equivalent circuits, it's mostly same with the transformer, but the difference in terms of operation and the final part of the equivalent circuit is the secondary side, rotor part. So in the transformers, the output gives us a voltage, but in here, the output, the rotor part, gives us a mechanical output, mechanical energy. So operation of induction motors, if we examine the system, because of the motor operation, we will convert the electrical energy to the mechanical energy. So we will start with the electrical supply. And we need three-phase voltage for most of the induction motors. Of course, we have single-phase applications also, but firstly, we need to examine the three-phase operation. So for the three-phase voltage applied to the stator, we have three different sources. Their magnitudes are nearly equal to each other as Vm, but their phase differences are 120 degrees. So standard three-phase voltage will be applied. Then the current will be produced, and the current will start to flow through the stator windings. And again, with the same manner, we have similar magnitudes as Im and 120 degree phase difference. And this current, as we discussed in the magnetic circuits topic, will produce a magnetic field. And this magnetic field, when we examine according to winding locations on the slots of the stator, also has 120 degree phase difference with respect to each other, because we have three phase winding groups on the slots of the stator. So when we examine the net total magnetic field inside the machine, we can see when our voltage flow through the time. So if, let's say, this is our voltage for one phase, when we are flow through the time axis, net or total magnetic field has also same magnitudes, but when we examine the angle, it's rotating on the counterclockwise. So from the electrical, in terms of magnetic field, we can produce a rotating magnetic field, but in the direction for the classical voltage application, our direction will rotate to counterclockwise. So the speed of the magnetic field rotation, when we examine according to, again, the slots. For example, let's say this is our stator, and we have some slots like this. And when we look from the other side, so slots are located like this, and for example, the winding will come to here and it will return back from here. Let's say this is the current direction. So current enters from here and goes out from here. And we have in one loop the current flow. So let's say the current directions of these slots are like this. So upper side has the current going inside, and below side the current goes out. So in such a case, when we examine the polarity inside the machine, we have two poles. They should be located like this. The reason of this one, each current direction change between the slots, we need to locate a pole. So when we examine the situation, only we need to locate poles in this part. So for example, for this machine, for such a machine, we can say the pole number will be 2. So P represents the pole number in the synchronous speed. Speed of magnetic field rotation in the stator of the induction motor can be calculated with this expression. 120 is coming from the unit conversion. It is not related with the three-phase. F is the frequency of our applied voltage, and P represents the pole number according to current direction and the number of slots. Then this rotating magnetic field will cover the rotor conductors and it will induce a voltage in them. According to velocity of magnetic field value, magnetic field density, and the length of the conductor, we can determine the value of induced voltage. And the rotor current flow produces rotor magnetic field through the system. And after that, when we examine the induced torque inside the induction motor, it can be calculated with the cross production of the rotor magnetic field and the stator magnetic field. K represents the motor constant, and BR represents the rotor magnetic field, and S is the stator magnetic field. So from here, we should understand BR and BS must be different from each other. So always there must be a speed difference to be able to create this cross production positive or different from zero in the induction motor. Because of this, we should define the slip, the relative speed difference of the induction motor. It can be calculated with the synchronous speed minus motor speed over synchronous speed as a ratio. Or with the RPM units, we can calculate with this expression, or if we know the radian per second equivalence of the rotational speeds, also it can be calculated with the same formula. Ws represents the synchronous speed again as radian per second, Wm is the motor speed, and Ws again represents the synchronous speed, rotating speed in the magnetic field. So between the N and W, we have only a unit conversion, so these two equations will be equal to each other. So briefly, slip explains the relative speed difference between the stator magnetic field, stator rotating magnetic field, and the rotor rotational speed. Thank you for watching.